Hey Alge, here are the notes for prime factorization and GCF. So let's first start off with some definitions. What is a prime number? If I say a number is prime, what I mean is that it is a whole number greater than 1 whose only factors are 1 in itself. All right, we'll get into more in a minute. A composite number is a whole number greater than 1 that has more than 2 factors. And a prime factorization occurs when a whole number is expressed as a product of factors, which are all prime numbers. So that's a whole ton of conversation, but one of the things I want to focus on is this word factors. What are factors? Well, they are smaller, I guess, pieces. So small pieces of something bigger. So if I say, well, this was a big factor in my decision, what that means is that it was a piece or a part of why I chose to do something. So when we talk about math and the factors of numbers, what we're saying is, can we break a number like 5 into smaller pieces using multiplication or division? Well, since 5 is only 1 times 5, there are no other ways that I could multiply numbers in order to get 5. But 10 is a little different. I can multiply 1 and 10, or I can multiply 2 and 5. So because I can multiply 1 and 10 to get 10, or 2 and 5 to get 10, that makes this number composite. And that is your second one here. It has more than 2 factors. So this is your first factor. That is your second factor. And the prime factorization is actually just this breakdown that you see right here. So it occurs when a whole number is expressed as a product of factors. So if I take the number 45 specifically, I'm going to break it down this way. 45 has a few different factors. It has 1 and 45. It has, 5 is the next most obvious one, but I'm going to see if 3 works. Yep. It's got 3 and 15. And then it has 5 and 9, and there's nothing else that one could be. So these numbers, or this set of numbers, are the factors of 45. But none of these are the prime factorization, because if you look at these, the numbers within these numbers can be broken down even further. For example, 9 is a composite number that can then be broken up into 3 and 3. So if I want to write the prime factorization of 45, I not only have to take 5, but I have to multiply it by 3. Notice, all of these numbers are prime numbers. So this would be the prime factorization for the number 45. So let's look a little deeper into that. First example here, find the factors of each number, and then we need to classify the number as either composite or prime. So let's just start by breaking down 32. And the way that we most often do this is in the form of a factor tree. So a factor tree looks something like this. You put the 32 at the top, and then you break it down as far as you can go. 32 is divisible by 2. If I divide 32 by 2, I get 16. 2 can't be broken down any further, but the number 16 can. It can be broken down into 4 and 4. And those two numbers can then be broken down into 2 times 2 and 2 times 2. So what we've essentially created is kind of like a little Christmas tree here. This one's a little lopsided on this side. But this is broken down into all the prime factors. This is a prime factor. This is a prime factor. All of these are prime factors. So if I want to write the prime factorization of 32, what I would say is 32 is equal to 2, which is the prime factor, times 2 5 times, or 2 to the 5th. So because there's more than just one factor of 1 and 32, because there's all these extra numbers, this one is actually going to be composite. However, if we look at 31 and try to break it down in the same way, we see that 31 isn't divisible by any numbers except for 1 and itself. So this one would be considered prime. What about the number 54 then? Well, can we break it down into the tree? I try to find the smallest number I could possibly divide it by. I see that's 2. 54 divided by 2 is going to be 27. I know that 27 can then be broken down into 3 and 9. 3 times 9 is 27. I know that 9 can be broken down into 3 and 3, but once I get here, I see that I can't break it down any further. So I have a 2 and 3 3s. Because I have more than just the numbers 1 and 54 like I did up here, this is considered composite. All right, I suggest you try example 2 by pausing the video, going through those on your own. See if you can find if those are prime or composite, and then when you come back, we'll try to figure out the prime factorization for each of those numbers as well. You can try to use my steps over here as a guide if you're interested. All right, hopefully you have paused the video and come back. So hopefully once you did these, you found that this number was composite, this number was composite, and this number was composite. Now, to find the prime factorization, we have to follow the same steps that we did over here, and then we'll take them one step further. So let's make our factor tree. 42 can be broken down into 2 and 21. 21 can then be broken down into 3 and 7, but we can't break them down any further. So once I've gotten them as small as I possibly can, what I'm going to do is I'm going to take each of these numbers and I'm just going to line them up. 2 times 3 times 7. This is the prime factorization for the number 42 because it is the prime pieces of that number. All right, let's do 200 then. 200 is going to take us a little longer, but it's totally going to work out. Now, I could break this down into 2 and 100 like I've been doing, but all of my trees end up pretty lopsided. So what I'm going to do is I'm actually going to show you a little different method. I'm going to start with a 10 on one side and a 20 on the other, just to show you that I don't always have to start with a 2 or a 3 or a small number. Because if I have a 10 over here, what I can do is I can break that 10 into 2 and 5, and then break down the 20 just like I did before, into 2 and 10, and then 2 and 5. Now, it doesn't matter if I go in order. The only reason I like doing it this way a little bit more is because then my factors are in order, whereas here, when I get to the end of each of my triangles or each of my branches, these aren't in order as much. But if I do the prime factorization here, I get 2 times 2 times 2 times 5 times 5. But I do not want to have to write this way every time. It's long, it's drawn out. So what I'm going to do is I'm going to say 2 to the third times 5 to the second. This is a much shorter way of writing my prime factorization. But we can also do it with negative numbers. So let's do it with negative 18. I'll do this one again with a little different flair. So I'm going to find that the factors of 18 are negative 3 and 6, or 3 and negative 6, whatever you like. And then I've got a 2 and a 3 here. Now, the only thing I'll say about this one is that I don't really like the negative 3 if I can help it. So what I'm going to do is I'm going to break this one into a negative 1 and a 3 so that when I'm writing my prime factorization, I can write this as negative 1 times 2 times 3 squared. That just allows me to not have the negative in front of the 3. I just prefer writing it that way. So what does it mean to factor a monomial? Well, to factor a monomial means to essentially break it into these pieces. So, for example, if we're going to factor these monomials, we're going to break them into as many small chunks as we can. We're going to do this two kind of ways. So we're going to break up the 32 itself, and we're going to break up the x squared. To do this, we're going to do, I'm going to do 2 and 16, 4 and 4, 2 and 2, 2 and 2. So I end up having 2 to the 5th, or 2 times 2 times 2 times 2 times 2, and x squared, which can be broken up into x and x. So if I wanted to show this in its factored form, we would have 2 to the 5th times x squared. We could pull something out of these, but I'm going to leave it in this form just to simplify. I'll give you a little bit of time to do number 2. See if you can do that on your own. Same thing that we did over here. All right, let's flip to the back side now. So now we're going to be talking about the greatest common factor. For integers, also known as numbers, it is the greatest number that is a factor of all of the integers. For monomials, it is the product of their common factors when each monomial is expressed in factored form. So what does this mean? Well, if we want to find the greatest common factor, the GCF, for each set of monomials, let's see what that looks like. So let's look at this first example. We'll come back to what does it mean. Let's factor those out into their pieces. We've got 2 and 6, 2 and 3. For 18, we've got 2 and 9, and 3 and 3. So these are their factors. So if I want the greatest factor that they have in common, I see that they have 2's in common, but they also have 3, which is greater than 2. So the greatest common factor of 12 and 18 is 3. However, this isn't the greatest composite factor. This is the greatest prime factor. This is not the one we're going to be mainly talking about. Notice each of these also has a 2 in it. So because I can take this as a pair, the greatest common factor or composite factor that they have overall is going to be 2 times 3, or 6. We are always going to want the GCF, not the GPF, not the greatest prime factor. So let's see about these next two. This is a monomial. Let's find the greatest common factor they have. First, let's start by breaking down 16 and 72 and seeing what they have in common. We've got a 2, an 8, a 2, a 4, and a 2 and a 2. And then we've got a 72, which breaks down into a 2 and 36, 6 and 6, 2 and 3. I know that's hard to see. And then 2 and 3. So my greatest prime factor would probably be this 2, because this one doesn't have a 3. But if I want the greatest common factor, I need to know what they're both divisible by. So they've each got a 2. I'm going to circle that. They each have a second 2. I'll take that. They each have a third 2. And that's all they have in common. Notice there's no other 2's over here. There's no 3's over here. So the greatest common factor between 16 and 72 is going to be 2 times 2 times 2, which is 4 and 8. That is what they are both divisible by. That's the biggest thing we can take out of both of them, to divide out of both of them. Now we have to look at their x and y and z components. X, y, z, 3. If we break these down into a factor tree, it's not going to get much better. So I just want to see what they both have when I look at them side by side. I notice they both have an x, so I'm going to take that. That is going to be part of my greatest common factor. I notice this one has 2 y's. I'll break that down, y and y. But this one only has 1. So because my second one only has 1, I'm only going to take 1 from my first term. That's what they have in common, is only 1y. And as far as z's, this one only has 1, while this one has 3. But I can only take as many from this one as I have in my first one. So I'm going to take, I actually have 2 in that one, so that means I get to take 2 from this one as well. I didn't copy this over correctly, sorry about that. So I get 2 z's, or z squared there, for that term. So now I've broken it up by the numbers and by the variables. When I put them back together, I find that my GCF is 8xy z squared. This is what I can pull out of both of them and still have nice numbers. So let's keep going. I encourage you to pause the video here, try these on your own, see if you can get them, and then come back and I'll walk you through them. All right, hopefully you paused the video, had a chance to take a look at these. So let's find the GCF of these. If I make my factor tree for 18 and 42, it's going to look something like this. 21, 37. I notice they both have a 2, so I'll take that. They both have a 3, I'll take that. But that is all that they have in common. When I multiply these together, it gives me the greatest common factor between them, which is 6. All right, let's do the same thing. 45 and 15. 45 breaks down into 5 and 9. 9 breaks down into 3 times 3. 15 breaks down into 5 and 3. I notice they both have a 5. I'll take that. They both have a 3. I'll take that. That's all they have in common, so I get 5 times 3 is 15. Now you might be asking, can I have a factor that is just one of my numbers? Well, yeah, you can, because technically 15 also has the factors 1 and itself. So because 15 is a factor of itself, it is the greatest common factor between those two numbers. All right, let's do the next 2 monomials. We break them down in terms of what number we can pull out of both. What are 28 and 4 both divisible by? If you don't like the factor tree method, you can also do it this way, where you just look at the 2 numbers and say, well, what are those both divisible by that I could pull out? I can pull a 4 out of the first one, and I can pull a 4 out of the 28, and I notice that I end up with a 1 and a 7, both of which end up being prime. Convenient, not necessary, but convenient. What do they have in terms of a's? Well, this one has 7 a's to give. This one only has 1 a to give. So I'm only going to take 1 because that's the number they have in common. Okay, this one has 1b and this one has 1b to take. So I'm only going to take 1b out. That's all it has to offer me. I did want to show you the one without the factor tree, but if you're super stuck on that factor tree, absolutely no worries. It's a great method. Oof, this last one is a little bit tricky because instead of having 2 terms, now we have 3. So we have to figure out what all 3 terms have in common. Let's start by breaking down those numbers. 12, 32, 60. We have 2 and 6, 2 and 3. We have 2 and 16, 4 and 4, 2, 2, 2, 2. 60 ends up having 6 and 10, which is 2 and 3, 2 and 5. So I have to see what they all have in common. I know for sure they all have a 2 in common, so we'll take one of those. I see that they all have another 2 in common. We'll take one of those. And then they do all have, they do not have a 3 in common. I thought this one had another one, but it does not. So there's nothing else I can take from this one. There's nothing else that they all have in common. So I end up just taking the 2's and multiplying to get 4. But we're not done. This isn't my greatest common factor because I also have to look at the variables they have in common. I'll do that down here. So in the first one, we have an x squared. In the second one, we have an x squared yz. The third one, we have an x y squared. When I look at all these, I see that they all have an x that I could pull out. This one can take one. I can take one from here. And if I take one from here, I'm left with none. So I only have one x in common. Notice then, these two have a y in common, but because it's not common with the third one, we can't take a y out. We can only take what all three terms have to give us. So common between these three terms is just going to be an x. When we take the common number from these three terms, it's just a 4. Put those back together, and my greatest common factor for these three terms is 4x. All right, I know that was a lot. Let me know if you have any questions.